LifeStack, the constitutional layer for the AI era. This presentation lays out the mathematical foundations for identity, consent, and governance in autonomous systems. At its core, LifeStack addresses a structural problem that the major AI labs have not yet prioritized. How do you make AI systems that are cryptographically accountable, consent-aware, and resistant to identity forgery, not as a policy overlay but as a mathematical requirement? The thesis is direct. AI without sovereignty is unsustainable. Conscience is the new compute. Consider the current landscape. On one axis, we have capabilities. On the other, autonomy. Traditional AI, chatbots, APIs, single-step tools sits below the governance gap. These systems rely on external API keys, treat identity as a static label, and execute actions one step at a time. They are manageable. But agentic AI, autonomous planners, multi-agent swarms, operates above that line. These systems plan independently, maintain short and long-term memory, and access tools autonomously. The gap between these two regimes is the agentic governance gap. Modern AI lacks persistent identity, making it vulnerable to cloning and impersonation. It lacks explicit consent boundaries, and it lacks cryptographic accountability. That gap is where LifeStack operates. Here is the specific failure mode. Consider a sequence of agent actions. Action A is valid. Action B is valid. Action C is valid. Each one passes its local permission check. But the compound outcome, outcome D, is globally unsafe. This is the residual leak problem. Permission systems suffer compositional failure due to unbounded agency. A sequence of locally valid, rule-abiding actions compounds into a catastrophic outcome. The key insight is that we must move beyond preventing a static paperclip maximizer objective. Safety in multi-agent environments requires governing the entire trajectory of actions to prevent Goodhart's law metric capture at the execution layer. Guardrails alone are insufficient. This requires structural governance. This comparison matrix frames LifeStack against the major AI labs, OpenAI, Anthropic, Google. The distinction is structural, not competitive. Their core business incentive is data harvesting and extraction. LifeStack's is data sovereignty and user control. Their liability posture is highly exposed: copyright liability, action liability, regulatory risk. LifeStack provides SPI-compliant auditability. Their governance verification relies on self-certified, opaque safety boards. LifeStack uses cryptographic and mathematical proofs. The synthesis: big labs are not competitors. Their structural incentives make it difficult to build this layer internally. LifeStack is designed to provide the compliance, trust, and AGI readiness infrastructure that complements their capabilities as regulation scales. The bioquantum editorial blueprint defines LifeStack's core identity architecture as a triple. S equals the tuple of C, K, and Phi. C represents semantic consent codons. These explicitly define permissions, boundaries, and lineage as an internal policy algebra. K is the post-quantum cryptographic kernel. It is designed to resist identity cloning via ring LWE lattice hardness. And Phi is the aperiodic Phi lattice coherence layer. It prevents semantic drift via a dynamically stable geometric representation. The foundational principle: identity is treated as a first-class mathematical object, inseparable from the agent's operational state. The architecture is designed so that copying, forging, or silently modifying identity is computationally infeasible. Layer 1 defines the consent codon structure. Each codon SeSAA is a triple of permissions, boundaries, and lineage. Permissions define the allowed actions, forming an internal policy algebra. Boundaries are hard constraints that strictly override permissions. They cannot be relaxed by the agent itself. Lineage records cryptographic issuer origins, timestamps, and jurisdictions, creating a verifiable chain of authority. The architectural rule enforced here is acyclicity. The directed acyclic graph structure is designed so that no codon can justify expanding its own authority. Boundaries cannot be overridden unless explicit lineage authorizes the expansion. This is enforced structurally, not by policy. This slide addresses a subtle but critical problem: semantic drift under continuous fine-tuning. Standard periodic embedding grids accumulate harmonic resonance. Over time, this resonance compounds into catastrophic semantic drift. The identity representation silently degrades. LifeStack's solution is the aperiodic phi lattice. By scaling identity embeddings by powers of the golden ratio, the system creates a stable, non-repeating spectral spread. Long-range order is maintained without periodic repetition. The practical consequence: minor tampering causes instantly detectable spectral shifts rather than silent, runaway drift. The system fails loud, not quiet. Layer 3 binds the consent codons to the cryptographic kernel through a tensor product, theta equals C tensor product K. The core assertion: copying model weights does not equal copying identity. The identity kernel is designed around three properties. First, worst-case hardness. Identity relies on ideal lattice hardness, targeting mathematical security even against future quantum adversaries. Second, non-commutative binding. The mathematical binding sequence is irreversible, preventing reordering of codons or bypassing of constraints. Third, anti-clone resistance. Identity persists cryptographically, making impersonation and unauthorized state cloning computationally infeasible. LifeStack governs learning and adaptation through the mutation repair cycle. The next state S sub t plus 1 equals the repair operator are applied to the mutation operator M applied to the current state S sub t. The cycle operates in 4 stages: mutation or update, validation check, repair and stabilize, then state commit. If an agent fine-tunes on sensitive data and violates a boundary, the non-expansive repair operator rewinds the drift, reasserts the codon boundaries, and stabilizes the phi lattice before the state is committed. The design ensures that violated states are not committed. Drift is corrected before it becomes permanent. LifeStack defines a named suite of 12 quantum algorithms designed for mid-scale hardware diagnostics, organized into 3 categories. The first category addresses identity and geometric stability. PhiQPE for quantum phase estimation to detect subtle spectral drift, QOverlap ID for state overlap testing providing non-classical clone detection, QCodon walk for quantum walks over the DAG to detect graph anomalies, and H-identity sim for Hamiltonian simulation of ideal identity dynamics. The second category covers cryptographic security. QRLWEID for post-quantum identity signatures, QKeyCheck using Grover-style search for mismatched identity states, Grover-bound for bounding adversarial search for identity collisions, and QCommit consent for quantum commitment and reveal protocols. The third category handles governance and drift detection. QSVM drift using quantum support vector machines to classify governed versus drifted states, QAE risk for amplitude estimation of boundary violation probability, VQCGovOpt for variational circuits optimizing governance policy, and QAOA repair for combinatorial optimization of exact semantic repair sequences. The LifeStack Edge Gateway enforces a strict principle: no raw data leaves the gateway. All outbound flows pass through privacy-preserving detection mechanisms before any data exits the system. 4 detection mechanisms operate in parallel. Destination traits analyze ASN, IP geolocation, and DNS resolver chains. Handshake fingerprints evaluate TLS and QUIC negotiation vectors without decrypting payloads. Flow shape statistics monitor beacon periodicity and packet size interquartile ranges. Schema-only signatures reduce structured messages to locality-sensitive hashes using SymHash. The architecture denies unverified flows unless accompanied by a zero-knowledge egress provenance token. The system proves compliance without revealing content. The mesh layer synthesizes 3 domains into a unified architecture: the epistemic substrate, causal reality, and the large language models built by major AI labs. Execution enforcement, hardware, APIs, and action routing. And governance admissibility. LifeStack's identity S equals C, K, Phi. The systemic scale synthesis requires that actions in long horizon systems must traverse all 3 layers. Epistemics do not define governance. Governance does not execute actions. This strict mathematical separation ensures complete auditability across the AI value chain and physically prevents the residual leak problem described earlier. When multiple agents interact, LifeStack enables federated consent. Agents dynamically form overlapping consent domains and intersection subgraphs, treaty clusters defined by the intersection of their consent codon sets. Mutual attestation requires that agents exchange public keys and validate each other's identity kernels before any interaction occurs. The result is emergent governance, ecosystems designed for self-regulating coordination. Cross-agent lineage is cryptographically verified to ensure bounded collective divergence. No shadow identities or unauthorized delegations can survive in the federated network. LifeStack architects a three-tier model for the economics of AI trust. Private mode, share nothing with zero-knowledge execution. Personalized mode, share limited, govern data for low-friction AI utility. Monetized mode, share specific data, enforce boundaries, and receive automated compensation. The stablecoin trust flow is designed to convert user intent through the quantum consent fingerprint algorithm into FATF and ISO-compliant stablecoin payouts. The model addresses the assumption that privacy destroys revenue. Users would control and voluntarily monetize their data via mathematically bound, compliant financial rails. The estimated total addressable market ranges from $50 billion to over $100 billion. Scaling with global AGI adoption. The roadmap proceeds in 4 phases. Phase 1, the API bridge for enterprise trust and audit. Phase 2, the sovereign sidecar for individual agent governance. Phase 3, the photonic hardware node for edge cryptography. Phase 4, the regulatory standard for global alignment. LifeStack is seeking strategic funding and enterprise API pilots, alongside regulatory partnerships to help define the governance standard. The future will not be sovereign unless we build it. LifeStack is the ground floor of AI governance infrastructure.